All right, in this video, we're going to go through the entire review guide for the Unit 4 test. Okay, so first thing we're going to work through is some naming and formula writing. All right, so for formula writing, for naming, we have our formula here, N2O4. So you do need to know the prefixes. So let's go ahead and write these out. So for 1, it's mono. 2 is di. 3 tri, 4 tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and then 10 is deca. So those are the prefixes. One key thing to remember when we're doing prefixes, if you have something where it's by itself and it's the first piece, we never use the prefix mono. So we'll do an example where you'll see that. Okay, so for the first one, we have nitrogen, and there's 2 of them, so it'll be dinitrogen. And then we have 4 oxygens. The prefix for oxygen is tetra. And then you have oxide. Now, when we do this, you notice you have something kind of weird here. You have an A and an O next to each other. There's another rule that says if this happens, if your element starts with the letter O and your prefix ends with A, we're going to just drop the A and take it just like that. So it'll be tetroxide. All right. For the next one here, we have P2F5. So P is phosphorus, and we have 2 of them, so it'll be diphosphorus. And then we have 5 fluorines, so it'll be pentafluoride. So for all of these, don't forget we're changing that ending to IDE. Okay, number 3, we have 6 nitrogens, 10 oxygens. So this will be hexa nitrogen. And then we have deca oxide. And again, we have that situation where we have an A and an O next to each other. We'll just drop it, so it'll be decoxide. So now we're going to do formula writing. Trisulfur means we have 3 sulfurs. And then octa is the prefix for 8. So we're going to have 8 fluorines. Carbon nanofluoride. So if you notice, carbon does not have a prefix. Because carbon doesn't have a prefix, there's no mono or di. That means it's by itself, and this is that situation. So carbon's by itself. There's only 1 of them. We never use the prefix mono for the first word. And then we have nanofluoride, so that's F9. Okay, tetraphosphorus. Tetra is the prefix for 4, so it'll be P4. And then we have heptoxide, so that's going to be hepta, which is 7 oxygens. All right. Number 2 says, explain the use of the prefix mono in covalent naming. So we kind of already did this. So a couple things. Mono, the prefix mono, is never used on the first atom. We always use mono on the second if it calls for it. And the third thing to remember, is that weird rule when we have something like oxygen. So we're going to drop the O. So we drop the O in mono before oxygen. Okay, we did some examples like that up above. Okay, number 3 says, based on their electronegativity difference, predict the type of bond that will form between each of the following compounds. So the first one is carbon dioxide. And for carbon dioxide, that's what? CO2. So for this, you're going to go to your resource packet, and you have a table of electronegativity values. You want to find the difference between these. These values should never be negative, so you always take the bigger number minus the smaller number. Okay, so in this case, when we look up our numbers, we have 3.44 minus 2.55. We get a value of 0.89. And if you look that up on the bottom of that table, there's a range, and that falls in the range of polar. Okay, let's do the same thing for CF4. So we look up those values. Okay, so when we find the difference, it's 1.43, which is for a polar bond. All right, the last one, BCl3, so boron trichloride. So we've got 3.16 minus 2.04, 1.12, and again, polar. They're not always going to be polar, but in this case they are. All right. So we're going to go through this table, and we're going to draw Lewis structures. We'll identify the VSEPR shape, and then the overall polarity. So for the first one here, I'm going to do it the long way first, and then I'll kind of speed it up for the next couple. Okay, so we have boron. Boron has 5 valence electrons, and then we have chlorine, which has 7, and there's 3 of those. 7 times 3 is 21. So we have 26 electrons. Boron's going to go in the middle, and then we'll just kind of surround it with chlorines. Everything gets single bonded to the central atom. So 2, 4, 6 bonding. So we have 20 left. Okay, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, I actually goofed. Boron is not actually 5. Boron is only 3. So let me just change my math here. So let's see, that'll be 24. There we go. That looks right. Okay, so when we go to do our VSEPR shape, we look at how many things that are attached to the central atom. So I have 1, 2, 3 electron zones. None of them are lone pairs. So this will be a trigonal planar. Everything that's attached to the central atom is the same all the way around. We don't have any lone pair on our central atom, so this will be nonpolar. All right, let's keep going here. So we'll go a little bit faster on these next couple. So for CO2, carbon goes in the middle. We're going to surround it with oxygens. Okay, so we're going to bond everything up. We end up needing double bonds here. So we have 2 electron zones. None of them are lone pairs, so this will be linear. Everything that's attached to our central atom is the same all the way around. No lone pair on our central atom, so this will be nonpolar. Okay. On this next one, notice we have a negative. That means we have one extra electron. When we draw our Lewis structure, we end up with something like this. Now, when you have an extra electron or one less electron, we always draw it in brackets with the charge on the outside. Okay, we have 1, 2, 3 electron zones, no lone pair. This will be a trigonal planar. Now, don't get confused here. We have a double bond and then we have 2 single bonds, but it's all oxygen all the way around. No lone pair on the central atom. This one will be nonpolar. Okay, on our last one here, nitrogen's going to end up in the middle. Iodine, iodine, iodine. And let's throw our lone pair around. Not our lone pair. Let's throw our electrons around. We have 2 extra left, so those are going to go on the nitrogen here. So we have 1, 2, 3, 4 electrons zones or electron regions on the central atom. One of them is a lone pair. So this is going to be trigonal, pyramid. And even though it's iodine that's attached, we do have a lone pair of electrons on the nitrogen. So this one's going to be polar. Okay, let's move on to the next one here. Next one says, using Vesper theory, explain the molecular geometry of water. Okay, so let's draw out a Lewis structure for this one. So the key thing to notice here is we have some lone pair on the central atoms. Okay, so the lone pair of electrons have a greater repulsion than the shared or bonded electrons, which pushes water into bent shape. So what's happening here, you've got these lone pair, and normally it would be linear, it'd be straight out, but these lone pair are pushing these down, which cause it to take that bent shape. Okay, number 6, rank the following forces from weakest to strongest. So London dispersion is only present in nonpolar. So London dispersion is that really temporary force. So you have a nucleus. I have 4 atoms on one side of the nucleus. I have 1 on the other. It creates a temporary dipole. So we have more negative on one side, less on the other. It creates a very temporary dipole. It's kind of sketchy. So LDF is going to be the weakest. And then we're going to have dipole-dipole. Dipole-dipole is a permanent dipole. It's a lot stronger. It's not sketchy. So it's going to be stronger here. And then you have hydrogen bonding. Now, just a real quick recap here. For hydrogen bonding, you have to have one of these 3 combinations. You have to have HF, HO, or HN. And an easy way to remember this is, kind of spells out phone. FON, hydrogen fluorine, hydrogen oxygen, or hydrogen nitrogen. One of those 3 bonds has to be in the molecule for there to be hydrogen bonding. Otherwise, it's just dipole-dipole. Okay. Explain the difference in boiling points between ionic and covalent compounds in terms of the strength of their bonds. Okay. So, ionic is the strongest. Okay, so ionic bonds are stronger than covalent bonds. Would help to spell this right. Covalent. It takes more heat energy. For ionic to boil. So, obviously, if it takes more heat energy, the boiling point is going to be higher. So, moving on. Identify which molecule has a stronger dipole moment, NF3 or BF3. So that's nitrogen trifluoride, or boron trifluoride. Justify your answer. All right, let's start by drawing our Lewis structures for both. So I think we did the nitrogen trifluoride already. Okay, and then we have boron trifluoride. Forgot to mention this earlier, but don't forget, boron is okay with 6. Boron only wants to have 6 valence electrons. So if you notice, counting around, we only have 2, 4, 6 from the bonds. All right, so boron trifluoride is nonpolar. It's the same thing all the way around. Nitrogen trifluoride has a lone pair, so it's going to be polar. Okay. So, the only way you're going to have a dipole moment is if you are polar. So since boron trifluoride is nonpolar, it will be weaker than nitrogen trifluoride. Okay. Use intermolecular forces to explain why the boiling point of HF, so that's hydrogen monofluoride, is higher than that of HCl or HBr. Okay, so remember for hydrogen bonding, so these are all polar because you've got different things. So you've got HF, you have HCl, and you have HBr. So they all look like they're the same thing. They're all polar because you have different things on the left and the right. For it to be nonpolar, they'd have to be the same. Think about it like a tug of war. If you have the same thing on both sides, one side's not stronger than the other. But for all three of these, you've got different elements on either side, different atoms on either side, so one side's going to be stronger than the other. Now, if you notice here, HF has one of those magic combinations for hydrogen bonding. Again, for hydrogen bonding, it's HF, HO, HN. So it meets that criteria for hydrogen bonding. So, because it's got hydrogen bonding, and remember, the ranking from weakest to strongest is London dispersion, dipole-dipole, and then hydrogen bonding. Because HF has hydrogen bonding, it's going to have a much higher boiling point. Okay, it takes more heat to make those boil. So, because it has the strongest intermolecular forces, it's going to have the strongest boiling point. Okay. Says, explain the difference for boiling points for the two compounds shown below. So we have acetic acid and methyl acetate. Those look absolutely terrible. Look at all those crazy things going on here. Okay, but just like the previous one, I want you to notice this one has a higher boiling point. It's also the only one that has hydrogen bonding. So both of these molecules are polar. So if you look at methyl acetate, we have HCl. We have, or sorry, not HCl, HC. We have hydrogen carbon, hydrogen carbon, hydrogen carbon, hydrogen carbon. All right, those are the only hydrogen bonds that we have. Okay, but it doesn't fit the criteria for hydrogen bonding because it's not HF, HO, or HN. It's not one of those three. So acetic acid is going to have a larger boiling point because it's the only one with hydrogen bonding. Methyl acetate is just dipole-dipole. Or that's the dominant intermolecular force. Okay, determine the IMF present between two molecules of HF. So let's draw this out. Okay, so for this one here, it's going to be polar. So automatically, since it's polar, you're going to have London dispersion, and you're going to have dipole-dipole automatically. Every single polar molecule has that. Now, does it have the criteria for hydrogen bonding? Does it have one of these three? Remember, it spells out phone. Yes, absolutely. So it's also going to have hydrogen bonding. So the correct answer here would be London dispersion, dipole-dipole, hydrogen bonding. Determine all the IMF present between molecules of HCl and H2S, which is dihydrogen sulfide. Good stuff. Put it on my cereal in the morning. Okay, so we have, let's draw these out. So we have HCl, and we have H2S, so like this. Okay, so these are both polar. So for the first one, it's not the same. So you've got hydrogen on one side, chlorine on the other. They're not the same, so it's going to be polar. On the second one, it's hydrogen that's attached, but you've got lone pair on the central atoms. So these are both going to be polar. And then we check to see if they have the criteria for hydrogen bonding. Okay. Remember, it spells out phone. Yeah, neither of these have that. So, because they're both polar, you're going to have London dispersion, dipole-dipole. No hydrogen bonding on this one because it doesn't meet the criteria. It doesn't have one of those three bonds. And that's it. Look at that, 24 minutes, record time. Good luck on the test.